Well, hello, CNBT 1342. This is week 4, exam 4, lecture. We're almost done. Wow, isn't this cool? Yeah. All right, we're going to start off with structural provisions under the code. No, you're not going to be a professional structural inspector after this course. This gives you some ideas of what has to take place. So let's define some loads. Now, I am an old structural and mechanical engineer, so forgive me if I go off into geek land. All right, so the structural design requirements, and you can read all this, all right, on your own. There are lots of structural design requirements. Snow load, rain load, live loads, dead loads, wind loads, seismic loads, you name it. There are all kinds of loads. If you took my CNBT 1311 course, you know that we went through a lot of stuff. Now, no, this is not a structural engineering course, and I'm going to try to make this as painless as possible. All right, so there's some things we need to know, okay? You need to know what the definition of a dead load is. You need to know what the definition of a live load is, and it's right here. All right, dead load's the weight of the construction materials incorporated in a building. Everything, walls, floors, roofs, ceilings, RTUs, rooftop units, AC system, piping system in here. Oh, you name it. Everything, it's a dead load. Live loads are produced by the use and occupancy of a building, not including the dead loads or environmental loads such as wind, snow, floods, and earthquakes. Okay? However, as a structural engineer doing a frame analysis on this, you still have to add the additional wind, seismic, snow, and rain loads to the building. Okay? But is it a technical live load? No. Okay? But it is. So, live loads are loads produced by the use and occupancy of a building, and not including dead loads or the environmental loads such as wind. However, from a structural engineer standpoint, we do treat wind, seismic, rain, and snow as a live load when we do our analysis. But according to Ching and the total intent of the code, he states it's not, but I disagree. Okay? But it's a fine distinction. So what would be the answer to the question if you were asked? Well, you've already got the exam, so you know I'm asking you the bloody question. So loads produced by the use of the building, right? And me as a structural engineer, I'm going to include wind, seismic, rain, and snow. Okay, but according to the text, it's the loads produced by the use of the building. So, if you want to make me happy, then add wind, seismic, rain, and snow. But make bloody sure you put the produced by the use of the building, because that's the guts of the definition. Okay, told you I'd get off into geek land. Sorry about that. All right, what are construction documents? Oh my God, here we have construction documents. Construction documents. It's everything. How's that? Construction documents, all right, let's look at here. See, I typed this down here. Plans and specifications, including your soils report to which the project was designed and bid to, are also considered codes, legal documents to which the designer, engineer, and contractor are legally bound to follow. All right? So, everything is a construction document. The codes, all right? If you had a variance from the authority having jurisdiction, That needs to be in your construction documents, okay? Y'all came to an agreement. Remember the interpretation versus the intent, and it was all documented that the local building code people said, yeah, you can do this Super Captain Billy Whiz-Bang thing, all right? So that needs to be in there. It also needs to be in your specifications. So everything is a part of the construction documents. And you will keep that forever. Forever. Did I say forever? I did. All right. Braced frame. A braced frame is a vertical truss, including a building frame system to resist the horizontal shear forces such as those imparted by wind or seismic. That's a braced frame. Okay? It's like a vertical truss. Okay? We talked about trusses in Cnbt 1311. All right. The World Trade Center was a bundled tube with cross braces in it, and it became a moment frame, a giant, tall moment frame. All right, and a bundled tube concept. So this is the definition of a moment frame. And if you have your test printed out while you're going through this video in this lecture, oh my gosh, you've got a bunch of points. Look at that. All right. Now let's go down to shear walls. Okay. A shear wall. A well designed to resist a wall designed to resist lateral forces applied parallel to the frame of the wall, plane of the wall. The plane of the wall. We talked about shear walls in CNBT 1311 if you took my course. All right. Load-bearing wall. Here's the definition of a load-bearing wall. Here's a shear wall. Here's a load-bearing wall. All right. It talks about the loading, the general rule of thumb for the loading. Okay. Your mileage may vary. Your mileage may vary. Okay. So, that's the definition in here. Okay. Now, we got to talk about some other things. Serviceability, general design requirements in accordance with one of several defined and approved structural design methods, such as the strength design method, the load and resistance factor method, the allowable stress method, and so forth and so on. All right? Now, this gives you some things about, well, with plaster and stucco, you want the deflection to be in this range. Other brittle finishes in that range. Flexible finishes in that range. Okay? This is a structural engineer's problem. Okay? Deflection limits are based on a table and also AI, the American Institute of Steel Construction, or ACI, American Concrete Institute, or your Precast Concrete Institute, or your precast manufacturer. All right. So serviceability. Okay. What is serviceability? So that definition's right in here. Okay. The structure is to be designed to limit deflections and lateral drift under anticipated loading. Load effects on the structure are to be determined by application of a rational analysis taking into account equilibrium of the structure, general stability, and short-term and long-term material properties. Nobody wants to have an office building floor that bounces up and down when people walk down the hallway, right? You don't want a building that sways a lot. You end up getting seasick, especially if you're on the upper floor. And these tall buildings and super high-rises, they do sway. But the sway is dampened to the point that hopefully the occupants don't sense it. If not, people will be getting motion sickness, freaking out that the building's going to fall over. We don't want that. That's what serviceability is. It's limiting your deflections and your lateral drift of the thing under anticipated loading. Okay? Another thing we got to worry about is the risk category. What is the risk category? All right? Or the risk factor. Okay? Factors noted in the structural chapters are typical buildings, values, and the loads. Okay, so really, boiling this down, what is the risk factor? Well, categories by importance of consequences of the failure. Okay? If this is a hay barn and nobody's living in it, and you get a wind that comes through and knocks over the hay barn, well, the hay bales are not going to sue you, right? No one's going to put you in jail for killing hay bales. Now, the farmer may be a little upset, and you may get sued because you didn't satisfy the design requirements, but it's not like a bunch of people are dead, right? Okay, so that's your risk category, okay, your risk factor. It's categories by importance of consequences of a potential failure, okay? So it's a big difference if it's a hay barn as opposed to a school full of children or an auditorium or a church or a residence or whatever where people are living in, correct? Okay, so here we go down risk category 1, risk category 2, and 3, and so forth and so on. And that's all in the code, and your mileage may vary depending upon the locality of your structure, right? Okay, all right. Anchorage. What do we mean by anchorage? We're talking about anchorage in regards to structures. Okay? That's the chapter we're in, right? Roofs are to be anchored to walls and columns are to be anchored to foundations to resist the anticipated uplift and sliding forces that result from the applications of the prescribed loads, whether from dead loads or live loads. Okay? So you got a wind load that comes through here. You want your building anchored to a good foundation so it doesn't slide off or tip over and rotate and flip over, right? So it resists uplift. It resists sliding and overturning of the structure. I mean, you don't want the building to slide. You don't want it to turn over, right? Okay. And you have load combinations. When you design a structure, you've got dead loads, you've got live loads, you've got concentrated loads. And here's a table of uniform loads and concentrated loads. These are rules of thumb. This is going to vary according to your locality and the type of structure it is. All right? But these are some rules of thumb, gives you some general ideas in here. All right? So a concentrated load is a heavy load that's not going to move. It's just something sitting on the structure. Could be a giant piece of equipment in here that's anchored to the foundation floor. Is a concentrated load. And then your uniform load, your uniform live loads, would be people in here walking around. You might have 20 people in here at a time, maybe have one person. But the concentrated load is calculated by the weight of the equipment and dynamic loading on the equipment. What if this is a compressor? You're going to have dynamic loading depending on what kind of compressor it is. If it's a reciprocating compressor, it better not be on a suspended floor. That floor will be bouncing up and down. All right. Now this defines what a concentrated load is. All right. All right, let's move on. Loads on handrails and guardrails. All right. Loads on handrails and guardrails. They must intermediate rails, and those not a handrail, are to be able to resist a load of 50 pounds on an area not to exceed a 12 by 12 inch, including the openings of the spaces. Okay. Handrail assemblies are also able to resist a single concentrated load of 200 pounds. All right. So how many pounds per linear foot can handrails and guardrails resist in any direction? Okay. Handrails and guardrails. right here. Handrails and guards are to be designed to resist a load of 50 pounds per linear foot, applied in any direction at the top, and to transfer this load through the supports to the structure supporting the guardrail. That's 50 pounds per linear foot. It's a uniform load, okay? Roof loads are going to vary. There are minimum roof load designs depending on your locality. Whether you got snow, you got to do a snow load. You got to do rain. What's your rain? How are you going to get the rainwater off of it? Okay. Now, snow is going to build up. We don't have to worry about that in Houston. Okay. And then you got interior walls and partitions. All right. So, going back up here, loads on handrails and guardrails, 50 pounds per linear foot. All right. Snow loads, we talked about that. Snow's a funky thing, man. Snow builds up. My son lives in Crested Butte. It's like 10 to 14,000 feet. Okay. They get 8 to 12 foot of snow up there. And the snow builds up on the roofs, and underneath the snow is an ice sheet. And sometimes that stuff sloughs off and falls and kills people. In fact, there was an old lady, I'm sorry, that was bad, not an old lady, an elderly woman who had an ice sheet slide off her roof in Crested Butte last year and killed her. So during the winter, they have to have people go up there and shovel the snow off the roofs occasionally if it builds up too much. And that's an interesting job. Okay. Again, you're not going to find snow load requirement down here on the Gulf Coast. You will find wind load that and rain and stuff like that. And the closer you get to the coast, you'll have an extra special structural code for the hurricane force winds. All right. And this talks about all kinds of stuff. Well, here he actually does show snow sliding from a higher slope roof to a sidewalk, and you're buried under here. So, I think that's pretty cool. All right, well, it's not really cool, but I mean, it does happen. All right, so let's look at wind loading, okay? I need to pay attention to this part of the video very, very carefully. Wind design is kind of interesting. All right, wind loads. They're designed to withstand a minimum of wind loads. Okay, now we had 125 mile an hour winds during this last Stormageddon thing we had here in Houston, and then the next week Temple got hit with an EF2 tornado with over 125 mile an hour winds and destroyed a lot of stuff up there. Now, we're not going to talk about tornadoes because they pull a vacuum and the houses usually explode outward. But a normal straight line wind, which we did also have, we had 85 to 100 mile an hour straight line winds out of that storm. And what's going to happen, let's say the wind's coming from this direction. Now, we went through this in CNBT 1311, but we're going to go through it again. Okay, this side of the structure, if you were in my class, you will remember that's positive loading. And this is positive loading. That's pressure, right? But when the wind comes up over the top, pushes on this, but makes the crest, and then this is the leeward side. The wind's still going. It's going around the building too. This is negative pressure. This is negative pressure. There's suction over here and pushing over here. You're pushing and you're pulling. So, wind load produces both positive and negative. It produces both positive and negative pressure on a structure. And that includes your window systems and everything else. Okay? So, positive and negative pressure. Positive and negative pressure. This talks about wind speeds are designated as basic design wind speeds. All right. But you better be looking at your highest wind speeds, or you're going to end up having these tall buildings and wind is sucked out of them, just like we had in this last Stormageddon. Downtown Houston was a mess. It looked like somebody dropped a cluster bomb down there. Okay? The surface roughness is what structural engineers go through to figure out, what that's doing to the wind speed, and trying to calculate how the wind's going to affect us. All right? So we got some small squatty buildings, we got tall skinny ones, we got this, and then we got this giant slot right in here. See this open space right in here? All right. So let's say the wind is coming, it's going, there's the crosshairs on the wind, okay? And the wind's going straight from the screen you're viewing this at, right in between those two buildings. Well, guess what's going to happen? If that straight line wind is 100 miles an hour, the wind in here is much greater than 100 miles an hour because of the Venturi effect. That wind's going to hit all these buildings. It's going to get pushed right through that little slot. And then based on the Venturi effect, that wind speed in that area in between those is going to be much higher than 100 miles an hour. And so how you calculate that, how do you guess that? That's what you pay the big bucks for the engineers for. All right? Okay. Next thing we need to worry about is seismic loading. Well, we'll talk about soils. In the next chapter, I think chapter 18, we will have a soils report to look at. But soil lateral load, okay? Basement walls, retaining walls. If the water table gets up, then this soil is going to liquefy. You'll have more loading on your wall here, okay? We talked about this in CNBT 1311. Soil pressure wants to overturn this cantilevered retaining wall, wants to make it slide. And if you have water, there will be a tendency for uplifting. All right. Flood loads. Well, there's not much you can do if it floods and water's moving fast. It's 62.4 pounds a cubic foot at whatever speed the water's hitting the structure at. It'll move concrete barriers across highways and everything else. Now, rain loads on the roof. We talked about this in a previous video. One of my buildings that housed one of my engineering firms that I worked in, we had a complete building collapse because we had one of those super duper rains, and the roof drains got clogged up, and the building manager did not manage that very well, and it pulled the trusses off the sidewalls, and they collapsed inside the building. Very bad. Very, very bad indeed. Earthquakes are weird, and we talked about seismic design in CNBT 1311. If you had me, you'll remember I had you read about the pagoda pole, and why the pagodas in Japan can resist the frequency that the earthquakes generate. Japan's in the Ring of Fire in the Pacific, and if you'll remember, if you had my course, we talked about the snake dance of the pagoda pole, right? Okay, so earthquake forces on a structure depend on three items, okay? Three items, all right? And here they are right here. Seismic forces on a structure by ground motion are caused by seismic, time-dependent responses. The response generated by the ground motions depends on the magnitude and the duration and harmonic content of the ground motions, the dynamic properties of the structure, size, configuration, and stiffness, okay, and the type and characteristics of the soil supporting the structure. Now, parts of downtown Mexico City are built on an old Aztec lake that they filled in. And so there's still a lot of water under the ground, and so when they get hit with a side shake earthquake down there, like they did many years ago, that soil liquefies, becomes like oatmeal, and the building's foundations failed and they collapsed. And so here are the three the three items that seismic forces on a structure depend on, that affects the structure, or I should say. And it depends on how the earthquake's going to hit you. Is it just a ground shake, so that building has to ride that frequency wave up and then stay, because when it subsides, that frequency is going to subside, it's going to come back down. So it's got to ride the wave up, and it's got to ride the wave down. If it's just an uplift and a bounce down, or it's a complete movement of a plate tectonic. I mean, seismic design is, it's a guess. How's that? I don't care what anybody tells you. They're making a good guess. All right? Now, where the soil properties are not known in sufficient detail to determine the site class D is to be used unless the building official or the geotechnical data determines site class E or F soils are present in the site. This has nothing to do with you as an architectural designer. This is all engineering geek speak. All right. Okay? So, that's all I'm going to do to you for structural design. This, if you want to know more, this is the structural design criteria talks about that for the seismic characteristics. If you're interested, read down through here, and you'll get more than you bargained for. All right, but again, we go back to the risk categories. Okay, what's the risk category? Remember what the risk category was? What's going to happen if it fails? Is it hay bales? Or is it children in an elementary school, right? Or is it people in a retirement home or a hospital? Okay. And your building configuration also goes into account for how it handles in the seismic. And vertical irregularities. Is the top part of the frame braced and the bottom part's not? Talks about a soft story, weight or mass irregularities, the geometric irregularities, in plane discontinuity, and you got a weak story down here and a strong story over here as a part of this, right? All of these are going to have a different harmonic effect, a different K value, stiffness value, a different stiffness value, K value, just like a spring. Okay, so they will all act differently with that harmonics going up through the building. Okay, and then how much redundancy is it? Deflecting and drift limits. How much does it gonna drift? Is it gonna drift over and bang into another building? Okay. All right. I think that's enough for your structural. And of course, you don't want it to overturn. This is an example of it overturning. This is an example of side shear. It's actually being pushed over. All right. I enjoyed doing dynamic analysis as a structural engineer. It was a puzzle. So you figure out your worst loading conditions and do your dynamic, your moment analysis through all of this. Of course, nowadays we've got fancy computer programs that do that, but we all had to do that. Used to have to do that by hand. That was fun. All right, let's see where we're at. How much time have we wasted on this one? Oh, we're only 30 minutes. Okay, fine. All right. I think we beat the structural design to death. Well, there's one other thing I want to talk to you about. Under seismic design for architectural, mechanical, and electrical components. All right. You got piping in here. This shows piping for a sprinkler system, but it's any piping. All right, and if you're having to do seismic design, your MEP guy, mechanical, electrical, and plumbing engineer, needs to also, if you're in a seismic zone, because you don't want these pipes to break if this stuff's stretching. If the building's stretching the pipe, it'll break the joints loose. Your suspended ceilings, just like in fire, we talked about the support wires. Well, here we have some lateral supports to keep the suspended ceiling so that it can ride that frequency wave. All right. Same with HVAC ductwork. Elements such as architectural veneers, cantilevered exterior elements, signs, building ornament, overhangs, canopies. This would be like maybe for an exit door. All right. This would be an exit door. The people would walk out, egress. Okay, all this has to be accounted for in the seismic design. Okay, now we get into special inspections and tests. All right, there are 5 areas. Okay, 5 areas that require I hate it when they don't do this page numbering thing right. They leave that page blank. This is 323. Okay. There are 5 areas that we need special inspections for. All right, special inspections. 5 areas. Manufacturer, the installation, the fabrication, the erection, and the placement of components, where special expertise is required to ensure compliance with the design documents and reference standards. Okay. Now, these inspections may be required. Pay attention to this. These inspections may be required to be a continuous inspection or periodic inspection, depending upon the critical nature of the process and whether the inspector can determine compliance without being present during the entire process. Okay? Now, continuous inspection means the full-time observation of work requiring special inspection by a project inspector who is continuously present in the area where the work is being performed. Periodic inspection means the intermittent observation of work requiring inspection by a project inspector who is present in the area where the work has been or is being performed and at the completion of the work. Okay? So we talked about the 5 areas. Now, there are 5 conditions where structural observations for structures are required. Okay? 5 conditions that structural observations are required, and these are them. The structure is classified as risk category 3 or 4. The structure is a high-rise building. The structure is assigned a seismic design category E and is greater than 2 stories above the grade plane. Such observations is required by the registered design professional responsible for the structural design, and such observation is specifically required by the building official, the AHJ. Okay? I have been the engineer who has designed projects and also oversaw continuous inspection of the entire construction of the project. We had a team of inspectors on site 24/7 monitoring every phase of the project. Every phase. Okay? All right. So we've beat up continuous inspection, periodic inspection, the 5 conditions where structural inspections are required, and the 5 areas which require special inspections. Now, under manufacturer, let's go back up under here. Under manufacturer, you may have to send an inspector. I, as an engineer, have gone to a manufacturer's plant and observed the testing of pumps and mixers and gearboxes and such as that. Then we've had inspection on the installation, fabrication under structural steel or pressure vessels. Then we've had inspections for the erection and placement of special components like HVAC and plumbing, etc., etc., etc. Okay? All right. Your specifications under ANSI, NAISC 360 may require special bolts. Now, structural steel bolts is a minimum of A325. And my structural steel inspectors and I would go out and look at the bolts, and we would check the torque on the bolts, the torque specifications of these things. We get mill certs for the steel that they're using, welding inspection reports if they're doing welding, etc., etc., etc. Okay. All right. That's pretty much the salient issues for Chapter 17. Now, this is a welded up frame. The World Trade Center was welded bundle steel where they would run what? 3 floors? 4 floors, 3 floors at a time of structural steel. So these welds can be visually inspected or they can be radiographed. That's all in the specifications in the code. They specify the filler metal that's being used, whether it's the E6011, E70, E70 series. That's under the welding specifications, the welding process. Concrete, we get mill certs on the rebar. Okay, anchor bolts. Well, these bolts come from Portland, maybe Portland bolt. Inspect the anchors and the mill certs. May have to do a pull-out test on them. Verify the use required of the design mix for the cement. We get the cement mix recipe from the concrete supplier. The structural engineer goes over that. Then we do the testing, water cement ratio, the 7 and 28 day test for the concrete. Okay. If it's pre-stressed or pre-cast, we get testing on that and inspection. All right, so these are inspection, and then use the same for masonry. Verify the slump test. Placement of masonry units and mortar. We got inspectors watching how much mortar they put in. Do they do the cross ties like they're supposed to? Is the mortar made up properly? Etc., etc., etc. All right. These are visual inspections. Okay. Special inspections for smoke control system. You may have to do a test. It's a fusible length. We'll come in here and throw some smoke bombs in there during a test and see if the detection system's going to kick off, and check that out. See if they kick in. All right, that's enough for 17. All right, let's go over to Chapter 18. Soils and foundations. We must have soil and foundation investigative report by a registered professional soils engineer to safely design and structurally engineer a building, period. we must have a soil and foundation investigative report by a registered professional soils engineer to safely design and structurally engineer a building. If you do a structural engineered building without a soils report, you're just not riding ahead. You're going to end up having a bad day. I'm serious. That's where you very first begin. No building inspector is going to approve. No building authority is going to approve it without the soils report. And the report must be approved by signed and sealed, must be approved and signed and sealed by the professional engineer. Okay? Now, for those of you who took my CNBT 1311 class last semester, my apologies that I did not have my soils report in that class. I couldn't find it, but I did find it. So this is what a soils report looks like. Geotechnical investigative report. Okay. All right. This was done by RAM Testing. This was for a project on Cypress North Houston Road back in 2018. Okay. Here's the contents of the report. Summary of the findings. What's the subsurface look like? Groundwater conditions. Where's the groundwater? This is all a part of the report. Everything in here is needed. Now, this report is in D2L. I expect you to go through it because there's some questions coming out of this report. All right. The field investigation. How many borings did they do? The laboratory testing. They get a plasticity index. How do they do all that? There's the introduction. Okay. There's the depth of the layers of the cores that they found. Let's see here. Let's keep going. Foundation recommendations. Pay attention to this. Foundations recommendations. This is what you're looking for as an engineer and the designer. What are they recommending? Well, one, they talked about drilled and under ream pier foundations. Okay, we can use those. And this is, if we're going to use those, this is our loading requirement. Okay, what will it hold up? How much that? The depth. What depth do we need to put them down? Okay. How many pounds per square foot will the soil at that depth? Here's the calculation formula that we can use by the registered professional engineer. We can use straight drill shafts if we want, if we design our straight drill shafts according to the soil engineer's recommendation. So that's the second type of foundation that's recommended by this report. We can use continuous footing and grade beam foundations if we want. All right, as long as we design it according to the following paragraph. So what is that? That's number 3. Straight drill shafts, drilled and under ream piers is 1. Straight drill shafts is 2. The third type is continuous footings and grade beam foundations. And there's a fourth type, shallow spread footing foundations. This is their recommendation. And if you don't follow their recommendations, you're on your own if something bad happens. And then even he has pavement recommendations out there, but that's not for the building. So, so according to this soils report, we can use 4 types of foundations for the building itself, right? Drilled and under ream pier foundations, straight drill shafts, continuous footings and grade beams, and shallow spread footings, right? Then we get down to the soils report, and we're looking for somebody to help us and join us in court if something bad happens, if we do it exactly like he says, and it goes bad, we get to invite good old Oscar Zavalia, PE, project engineer, PE, professional engineer, state of Texas, professional engineer. There's his license number, okay, 93701. He gets an invitation to go to court with us if something bad happens, okay? All right, so, and if you're working with a registered professional engineer or registered architect, go to the state registration board for professional engineers and architects and plug in that number and the name, and they can tell you if they're still alive and they're still practicing, or if they have been sanctioned for something. So that's licensure. Architects have it, registered engineers have it, and just like your plumbing license and your electrical license. Okay. Now here's a site index. Here's a site map. There's the old Waffle House, and here is the detention pond, and here is the building site that we want to do, and here's an asphalt parking lot. So there's boring 1, boring 2, boring 3, boring 4, and boring 5. And here's the log of the borings of B1. Okay, the depth in feet. So you got sandy lean clay on top, which is hard tan, and here's all the gobbledygook that soils engineers and structural engineers get all excited about. Yeah, plasticity index, plastic limit. Oh my goodness, how much did it pass the sieve? Oh yeah, I know y'all were really excited about sieve test. Now down here below 5 feet we get into clay and hard clay and tan, and then down at 15 feet we got silty sand and tan, and the boring was terminated at 20 feet. Okay, all right, and back in the report it talks about any groundwater that they found or anything else. Okay, all right, so this is what a typical good soils report looks like, and I know y'all are like super excited about this. I know you are, I can tell, especially like you on the front row. I can see you smiling. So anyway, wait a minute, I don't see anybody on the front row because this is an online class. Wow, I must be talking to imaginary people. Okay, well anyway, let's go on to chapter 19. How's that? Okay, enough of the soils report. Just remember the recommendation of foundations for the soils report and who we get to invite with us to court if something bad happens. Good old Oscar Zavalia. All right. All right. And there's drainage and groundwater concerns. There's all kinds of stuff in your soils report. Everything that a good soils report will have. And this is a good one. I used to use McBride Radcliffe a lot. I don't even know if they're still in business, but that's in the Stone Age. All right. Got to start. First thing you do is get a geotechnical report. All right. Okay, enough of that. Okay, let's go to chapter 19. 19? Yes, chapter 19. Okay. Chapter 19. Well, here's 18. We hadn't finished really 18, have we? Not really. We must have a foundation soils report. And this goes through and tells you, on that report he talks about, so if you have a retaining wall, if you're going to have a retaining wall, he would have recommendations. And you get with your soils guy, say, okay, what are you going to be doing? We're going to have an open pit with retaining walls, or we're just going to have a building on drill piers or whatever. And they put that in the report. They address the water table. Maybe you need a French drain, foundation drains, backfilling recommendations, because when you backfill and compact this, you're adding super extra forces onto this wall. If you got a high water table propensity, you may need to waterproof it. We went through all this in CNBT 1311. Allowable load bearing values. It's pushing down, the soil's going to push it up. Resist it. Keep it from sinking. That's what he was talking about. That 5,100 pounds per square foot at a certain depth in the report. All right, footings and foundations, all of this stuff. Now, we don't have a lot of this down here. Most of our stuff is pretty well flat. But in areas that you have stepped, then the soils report has to address what's called the angle of repose. If this building is going to push this much force on the soil, you're going to have lateral forces also at angular. So how far away from this edge can you put that building without collapsing it and having a mudslide like they do in California? Okay. Footings and foundations, all kinds of stuff in here about footings and foundations. All right. Deep shafts, there's your drilled and underream piers, and that's your straight shaft. All right. Building materials and systems, 19. All right. Concrete. Start with concrete. Start with concrete. All right. Concrete. Chapter 19 is based on standard ACI 318, which is the Bible for reinforced concrete. As a structural engineer, I had the entire library of ACI 318. I was even on an ACI 318 committee in the ancient days of yore. So, ACI, American Concrete Institute. American Concrete Institute. The ACI code that governs this is ACI 318 again. Okay. I already gave you the answer. Boy, am I really giving stuff away, aren't I? Okay. Jesus. That's all right. That's okay. All right. Under concrete testing, cylinder test. We talked about inspections, right? So you're going to take a slump test out there on the car. And we talked about slump testing. I even showed you a video in Cnbt 1311. The cylinder test. There's a set of cylinders that are broken at 7 days and at 28 days. And you're always looking for your 28-day strength, which is your ultimate strength. That's theoretically when the concrete is at its strongest. 7 days gives you an idea when you can get back on that slab and start continuing construction. Now, when you're doing a bunch of high-rise stuff where you're having form work, you're always looking for early strength so you can remove the forms underneath and start building the form work on top. And at some point in time, then you can start wrecking the forms underneath, but you still got forms up here. But you got to be really careful and balance at 7 and 28-day strength. And it may reach its ultimate strength, say 5,000 psi concrete at 28 days, but that doesn't mean it's totally cured. Concrete will continue to hydrate and cure. The dam up there at Branson, Missouri, I forgot the name of the lake. That dam was built during the workforce stuff during the Depression, and it's still curing. The concrete down at the base of the dam is still curing. Big hydroelectric dam. If you ever get to Branson, take the tour through that. It's really cool. All right. Okay. So 7 and 28 days. Construction joints. This is a repeat from 1311, Cnbt 1311. All right. What kind of construction? What kind of construction joints do we have? Okay. We have construction joints. We have contraction joints, and we have isolation joints. Those are your three major construction joints. Construction, contraction, and isolation. All right. Reinforcement, spiral ties for your vertical reinforcement for a spirally tied column as opposed to a square tied column. These are stirrups for a beam. Okay. For the sake of this course, you pay attention to this. Your bar spacing. It's 1 bar diameter or 1 inch minimum for flexural members, and 1.5 times the bar diameter or 1.5 inches minimum for compression members. Okay? Now, why is this important? Well, what's concrete made out of? It's made out of cement, water, fine aggregate, and coarse aggregate. And you've got to get that mix, including the coarse aggregate, in between and around the reinforcing bars. And if you get these bars too close together, you won't be able to get all that concrete and the aggregate around it and compacted, right? Okay, so that's very important. Sometimes people try to save money and space by making these concrete beams deep and narrow, but by the time they get all that reinforcement steel in there, you cannot get the aggregate and the mix around all of that to get a good, dense, mixed concrete. And if you don't get it consolidated in that formwork, your structural member is not going to be near as strong as it needs to be. All right. All right, what else do we need to take care of? How about the minimum concrete cover for concrete footings, permanently exposed and cast against the earth? 3 inch minimum concrete cover. If it's cast against the earth, 3 inch cover, 3 inches cover for concrete, okay, cast against the earth. Now, this is where I disagree, but I use the belt and suspenders report. Structural plain concrete, and this is kind of oxymoronic. I don't consider any concrete structural if it doesn't have reinforcing steel in it, but I'm a geek old engineer, okay? Is it ever permissible to have unreinforced concrete? Well, this says yes. It is acceptable to use plain unreinforced concrete under certain conditions, but only for simple structures. Well, what in the name of Zeus is a simple structure? Concrete's expensive. The most expensive part of concrete is the farm work. You're going to spend more money on the farm work, if you paid attention to my CNBT 1311 course, than you are for the actual concrete. Okay? So yes, you can do a simple structure like this. If this was a small planter retaining wall, this has a seal on it. It looks like a seal plate, and you're going to put a wall studs on it. You do that, I'm going to fire you. I will fire you in a heartbeat. Okay? At very minimum, you need temperature steel, just to keep it from from having shrinkage cracks in it. All right, but according to the book and according to the code per 1906, yes, it's acceptable to use plain unreinforced concrete under certain conditions, but only for a simple structure. And I guess if it doesn't crack, then you can still say it's a simple structure, okay? Minimum requirements of ACI. But if you go to ACI and look in ACI 318, it's going to tell you to use a minimum reinforcing to address your temperature changes and shrinkage cracking, which is what we call shrinkage steel. Minimum percentage of reinforcing. Okay? So, don't do plain concrete. But the answer is yes, it's acceptable. It's permissible to have unreinforced concrete. So, yes. But don't do it. Okay? So, I already gave you the answer to the problem, the question. That would be question 8 on exam 4 under chapter 19. All right, Merry Christmas. All right? But don't do it. Use the minimum temperature steel under ACI 318. Because this stuff, when it starts to hydrate, in the water mixes, I mean, it starts to harden up. The calcium carbonate, it starts getting hard. It's going to shrink a little bit. Okay, the heat of hydration and the shrinkage, and I know I'm going into geek land for you people, but it's going to crack, and you don't want temperature cracks. To use temperature steel, minimum percentage, okay? All right, enough of that. I'll get off my soapbox. So yes, the answer to number 8 under chapter 19 of exam 4, the answer is yes, but don't do it in real life. Okay, Merry Christmas. All right. All right, let's go to masonry. We're going to skip aluminum. Aluminum's aluminum. You know, I mean, the code's going to tell you window wall systems, glass systems. We went through all of this in CNBT 1311. You get with your manufacturer of this, okay? They will tell you what code this thing's rated under. And your local authority is going to also tell you, okay? All right. So under masonry, there's all kinds of masonry. We beat the heck out of masonry in 1311, didn't we? Okay. All right. Masonry design. Okay. See, this may take, you may require continuous inspection. All right, to make sure your masons are actually putting the straps and stirrups like they're supposed to. All right. Okay. All right, there's 3 basic design methods for masonry. Okay, this is a hint. If you got that test printed out, you know what's coming next, right? All right, the 3 design methods for masonry is allowable stress, strength design method of masonry, and the empirical design of adobe masonry. Yeah, wow. Okay, wow. Adobe masonry. That means you take adobe blocks, stack them up, hope they don't fall down, right? No, I'm just joking. All right. Well, not really, but I am. Okay, this is described in that section code. All right. The strength design is in these 2 section codes, 2106 and 2108, and it's also referenced in the standards of this, the TSMK. And then the allowable stress has its own code up there under 2107. All right, and so forth and so on. All right, allowable stress design is to be, for this, is a structural design method that's based on some of the oldest principles of structural engineering. First, loads and forces act on a structure are determined, then the ability of the structure to resist those loads. Strength design is based on the principle of shifting some of the safety factor from the material properties by using factored loads. In other words, maybe it'd be a 1.4 of your 1.7 of your live load and 1.4 times your dead load. Okay, that's strength design. Okay, allowable stress is the actual stress that's allowed by the material and the cement and how it's tied together. This is engineering stuff. You designers aren't going to have to worry about it, except for the sake of the exam, sake of this course. Then these are the 3 methods: allowable stress, strength of design, and empirical design of adobe masonry. All right. I'm not going to make another video. This thing can just go on. It'll be a long video. You'll get over it. All right. Steel. Structural steel designs fall under the National Code of the American Institute of Steel Construction. The design of structural steel is under this code. Okay. There it is, American Institute of Steel Construction, AISC. That's that big book we structural engineers use for doing structural. It goes through details, connections, what's allowable, deflections, all the different shapes. Then again, this is not a structural engineering course. All right, it's a code course, but it's AISC 360. And there are other separate sets of specifications for structural steel design, depending on the design method used, load and resistance factor design, or allowable stress design. Bolts, welding, AWS, American Welding Society codes for the type of welding and the welding processes. Those big box girders that I designed for the Hardy Toll Road are way outside of the norm. Still hadn't fallen down over those railroad yards, and I had to do I was the engineer also that did the welding process, the welding process design for those. We had to preheat the upper flanges. Those things are all welded up. Anyway, that's not a part of this course. I'm sorry. I'm getting off into silly land. All right. So AISC. So I think we can say goodbye to chapter 19. Your trusses, if you're using trusses, you get with your manufacturer, they'll also be under AISC, and the Steel Joist Institute. The Steel Joist Institute, okay? And the manufacturer who's building these under the Steel Joist Institute will give you your allowable loads and the spans and deflections and such like that. But again, you're not engineers, you're designers, okay? But Steel Joist Institute controls that. The American Iron and Steel Institute controls your cold formed metal joist and metal frames and studs, like for instead of wood you'd use cold formed steel. We talked about that in CNBT 1311. And if I ever get to design a house, I will not have a wood stud in the thing. It will be heavy gauged, structural, cold formed studs and floor joist. Foam filled with closed cell foam, and because those of you who are in CNBT 1311, and on the outside finish at a very minimum would be hardy plank. All right, we're not going to go through wood burns, and if you want to, you can read through all this. The standards for wood, if you're using engineered wood products like prefabricated joist and trusses, your manufacturer, again, just like the steel joist, have a association that governs them. Your local building code will govern what you can use and what you can't use. All right, so that's enough of this. All right, more details, all the way to page 56. Connection details, this is all out of CNBT 1311. Ching is really repeating himself on this. All right, so we're done with chapter 19. Let's go on to chapter 20, and we'll finish this section, this week 4. And okay, plumbing systems. If you don't get anything at all out of chapter 20, okay, chapter 20 is not all that long. It's just got a lot of tables and stuff in it. Okay, here's 21, elevators and so. All right, let's go up here and we'll finish this video off. Okay, I've done this for you. It's kind of weirdly written. All right, number 1, the designer must consider the following 4 fixture elements for a proper building design: the number of fixture units for each gender, the accessibility requirements, the presence of single-use or gender-neutral toilets. There's your 4. Okay, number of each gender, accessibility requirements is 2, the presence of single use is 3, or gender neutral toilets is 4. All right, number 2, total occupant load for determining plumbing fixture count starts with the egress occupant load IBC 10, okay, divided by 2, the occupancy load. All right, divided by 2 equals the fixture demand for male and female. All right, all that's up here. Okay, it's IBC chapter 10. Okay, which is then divided by 2 to determine the fixture demand for the occupants. The normal rule of thumb, is 50% female and 50% male toilets. Now, anybody who's gone to a concert or ball game or anything in a big stadium know that there's always a line coming out of that female bathroom, right? Okay. Now, but the rule of thumb is 50% female and 50% male. There can be a case. There can be a case where there would be a different ratio. The designer will need to get with the local authority having jurisdiction, the building code people, to show data for a different ratio. If the AHJ agrees, then the ratio can be different. You might want, I don't know, 70% female and 30% male. But if it's an all-male locker room, then you may not have this ratio. But you have to get with your authority having jurisdiction and make a case for it being different. But it can be different. Now, the IBC table 2902.1 is maintained by the International Plumbing Code. That's who controls all of this. Okay, you'll find that down in here, and all of this gobbledygook is up in here. All right, Merry Christmas. All right, I've told you I was going to try to make it as painless as possible. All right, so guess what? That ends week 4, and that ends the review also for exam 4. Now, what are these tables? It's 29. Let's look at the tables. 2902.1. See? Assembly. There's male, there's female. That's a ratio. Okay, what kind of assembly is it? Well, if you're going to have more females and less males for whatever reason, I don't know, maybe it's an all-girls school assembly room, okay? Then you make a case for, hey, you know, this is an all-girls school, or this is a nunnery or a convent or something, okay? A nunnery, convent, well, that was bad. Anyway, then you'd make a case for having more female toilets than male toilets. But that's you as a designer getting with the authority having jurisdiction. And that's what these tables all represent. Okay? All right. Minimum plumbing fixtures, it talks about all of that. All right. Last week, we'll be doing elevators, systems, and such as that. So we're going to end this video here. This one's running, what's it running? An hour and 13 minutes. We'll survive. All right. We'll see you on the next one. Enjoy week 4, exam 4.